So today I'd like to tell you about some new research from our lab on space-time, and in particular, how time and space interact in response to motion. Okay, so I want to start off with Galileo's relativity principle from 1632. So Galileo gave an analogy in his famous book of a ship moving fast on the ocean. And but if you you know on the deck you can tell you're moving fast, the wind is going past you. But if you look below deck in a cabin, you can't actually tell that you're moving. So like the water's going to drop straight down, smoke's going to rise straight up, butterflies are going to go fly back and forth. And Galileo was getting this analogy because he was trying to explain to people how the Earth could be rotating and then moving around the sun, and you wouldn't notice the difference. But this analogy turned into Galileo's relativity principle, where it was stated that the laws of physics apply equally to all inertial reference frames. An inertial reference frame is like, let's say this room is a reference frame that's moving in a linear path at a constant velocity. But if you think about it, this is a pretty big claim that came out of this analogy, because Galileo's entire analogy was just based on trapped air and the conservation of momentum. And it wasn't until 1905 that this relativity principle was greatly solidified by Albert Einstein. And I have to go over a few of these features of special relativity so you can understand the talk. So one feature is the speed of light is independent of the motion of its source. So here's an analogy. Here's somebody going in a car at 30 meters per second, and they're throwing a ball out of the car at 20 meters per second. So to a stationary observer who's watching both of these things, the ball is actually going at 50 meters per second because it was going 20 from the car, but it also picked up the car's velocity of 30 meters per second. But if somebody were to shine light out of the car, the light's going to go at the speed of light, which is 299,792,458 meters per second. And it doesn't matter that the car is going at 30 meters per second, this light's not going to go any faster. It's always going to go at its speed of light, regardless of what the motion of the source was. And then another feature of special relativity is that for moving objects, time is going to slow down. There's time dilation, and length is going to contract in the direction of motion. So here we see a spaceship at rest, and it's got normal passage of time. But it's in motion, its length is going to contract in the direction of motion, and time is going to slow down for anything on the spaceship. And then another feature of special relativity is all observers are going to measure the same speed of light, and that speed of light is c. And this is actually really surprising, and so we have to go over exactly how this works. So here's the moving perspective. Here's a moving observer who's in a spaceship. The spaceship is moving. And we're going to be looking at light going in the forward direction from the back of the cabin to the front of the cabin, and light going in the backward direction from the front of the cabin to the back of the cabin. And what you're going to notice is that this light is going to go equally, and it's going to end up at the same time on the two directions. So that may not surprise you, but it is sort of surprising if we take the perspective of the stationary observer. So in this case, light's going to go in this spaceship is going to be moving relative to the stationary observer, and light's going to go in the forward direction. But what's going to happen is so here's the moving spaceship, and as light goes in the forward direction, the front of the spaceship is going to go away. It's going to take longer. On the other hand, when light goes in the backward direction, the back of the spaceship is going to hit it first, and the light's not going to go that far. So let's focus on this forward direction first. So the light's going to start, and here we're tracking the light path, but it takes a while for the light to hit the front of the spaceship. And now let's look at the backward direction. So in the backward direction, the light's going to start here, but it's going to hit the back quickly because the back was moving toward the light. So now, this stationary observer is trying to understand what the moving observer on the spaceship is thinking, or how he can calculate the speed of light. And what you have to think about is the moving observer is going to say, well, the distance was this cabin. So this distance is this green arrow here, green distance. But the stationary observer, like, well, in the forward direction, the light took this long to reach it. And so why isn't the moving observer taking this distance divided by the time, which is very long, and coming up with a slower speed of light, so slower than c? And then in the backward, when light's going in the backward direction, the distance is still the cabin as far as the moving observer is concerned, but the amount of time it took is very little. And so if you take the distance, this distance in the moving frame divided by time, the speed of light should be faster than c. Okay, so this is a pretty surprising result, and there's no way that this actually came from slowing down time and length contraction. It didn't come from these. Okay, there has to be another feature of special relativity that's gonna cause this, and that is that for moving objects, time is offset with distance in the moving frame, and we're going to call this differential simultaneity. Okay, so this is the way it's going to work. So for a moving observer, and they have clocks going along this cabin, they're synchronized with each other, and so all the clocks are at 12 o'clock. But these are actually special clocks. These are nanoseconds, and these are nanominutes. And so and the whole cabin is 15 light nanoseconds, which is how much light goes in 1 nanosecond in distance. And so when the light starts, the clock says 12 o'clock. And then when the light arrives, the clock says 12:15, which makes sense because it took 15 nanoseconds to go across, but the distance was 15 light nanoseconds. So that's the speed of light as being c. But let's take a look at this from the stationary perspective. What the stationary observer sees is that these clocks are not synchronous. That in fact, the front clock is at an earlier time than the back clock at the time when the light was emitted. Now, the stationary observer is going to see that the light's going to hit at 12:15. But the reason it hit at 12:15 was because it started off at 11:30. So, and this is actually important because everybody has to agree on certain things. So everybody has to agree that the speed of light started at 12 o'clock. Like no matter what observer going in what direction and what speed, they're going to see when the light's coming off, this digital clock is going to say 12 o'clock. And they're going to see that when the light hit this side, the clock said 12:15. And that's what's going to happen here. The light's going to go off at 12 o'clock. The light's going to arrive at 12:15. But the reason this happened is because in the moving frame, time is offset with distance. Okay, so you can ask yourself, why is time offset with distance in special relativity? And to understand that, we have to go to the basis of special relativity, which are these 4 Lorentz transformation equations. So this thing basically, everything comes out of these 4 equations. So this is the LT coordinate equations. There's one for time, there's x direction, x distance, and remember that the x is is where movement is in. There's y direction and z direction, and what I want you to, and so the way these work is there's like a t prime, which is the time in the moving frame. The prime means it's in the moving frame, and then the unprimed is the time in the stationary frame. And the surprising thing is that this time equation has an x term in it. So it has a distance term in the equation. And that's surprising because if, let's say that the time is 0, well, the time in the moving frame is not 0. And if you increase the distance, well, the time in the moving frame is going to increase. And you increase it more, it's going to increase even more. So suddenly time is now dependent on distance. So let's see to understand this, you sort of have to understand a space-time diagram. It's a little bit complicated, but not really. So the y-axis is time. Okay, so we're going to make it in seconds. And the x-axis is in distance. And we're going to make it light seconds. So this is how far light goes in 1 second. And so the black is the stationary perspective, and the green is the moving perspective. Okay, it's the moving And so here we see the x prime axis in the moving frame and the time axis, the t prime axis in the moving frame. Now the t prime axis is at an angle because these two frames are moving relative to each other. So that's all this angle means. But this x prime axis is actually telling you that time is offset with distance. The way to think about it is, let's consider the stationary x prime axis. It's at time zero. And everything along it is at time zero. So like 1 light second is at time zero, 2 light seconds at time zero, 3 light seconds at time zero. They're all at time zero, right? Because they're here at time zero. Well, this x prime axis in the moving frame is also at time zero in the moving frame. So at 1 light second, it's at time zero, 2 light seconds, time zero, 3 light seconds, time zero. But look, while they're all at time zero, they're all at different times in the stationary frame. Okay, that's the offsetting of time with distance. And it's going to affect what's simultaneous. So here's two events that occurred that are simultaneous for the stationary observer. They're both occurring at 2 seconds. But they're not simultaneous for the moving observer. The other thing I didn't tell you was this x prime axis determines how you read off time in the moving frame. So time, because this x prime axis is slanted, time is read off slanted. So this event occurred at time 1. And then this event occurred at time 2 on the t prime axis. Okay, so things are not simultaneous. And then here, both of these events occurred at time 1 on the moving frame, but they're not simultaneous for the stationary observer. Okay, and this not being simultaneous is why we're referring to this as differential simultaneity. Things are not simultaneous for special relativity. So here we're looking at a moving platform, and it's going from 0 to 1 light seconds in the moving frame. And what we're looking at here are earlier manifestations. It's moving like this along that track. And this is an earlier time, it's a later time, a later time, a later time, and this is the latest time. Okay, now we're going to put a stationary observer at the origin at this time 0. And he's going to be looking across. Now, the stationary observer cannot look in the future, and the stationary observer can't look in the past. The stationary observer at time 0, it's going to be looking at time 0 and see what it sees. And what it sees is this platform is now this length. So in the moving frame, the platform is 1 light second, but here he's going to see its length contracted. It's only 0.8. So it's length contracted. So he sees that. But what he also sees is that the front of this platform corresponds to this earlier time for the platform. And the back of the platform corresponds to the later time for the platform. And everything in the middle corresponds to different times for the platform. So if you were to look at synchronized clocks in the platform, it would be a later time at the back and an earlier time at the front. Okay, and that earlier time is minus VL prime over C squared, which is velocity times the distance in the moving frame divided by the speed of light squared. And we're going to call that the relativistic time offset, or the RTO, and it's minus VL prime over C squared in the forward direction. But if you consider from the forward direction to the back, it'll be plus VL prime over C squared. Okay, so we also have to introduce another transformation. So this is the absolute Lorentz transformation, and it was first described by Eagle in 1938, rediscovered by Tangerlini in 1958, which is sometimes it's called the Tangerlini transformations. It actually has multiple names because it's been rediscovered multiple times. And it also has these same four equations, and notably the x equation, the y equation, and the z equation are all the same. They're just the same as special relativity. But the time equation is different. Okay? So if you look at this x term that's in the LT time equation, there is no x term in the alt equation. And because there's no x term, time is not going to be linked to distance. If it's time 0 in here, it'll be time 0 in the moving frame. And no change of time distance is going to change that. So we actually, me and my collaborator Riju Balachandran, we actually had the first full plotting of this alt Before that, there was just only one paper that it had like 3 lines, 1, 2, 3, and we couldn't understand that. So we plotted it out, and we had the first publication of that. So what you can see is that for alt, the x prime axis and the x axis both overlap. And because they're both horizontal, all of these times are also horizontal, are also read off horizontally. So let's look at some aspects of that. So here we see event A and B are simultaneous in the stationary frame, but they're not simultaneous. This one's actually at time -1, and this one's actually at time +2 in the moving frame. But here for alt, events A and B are simultaneous for both the stationary and the moving observer. And then there's also differences in the one-way speed of light. So for special relativity, let's say this is a platform going from 0 to 1. So it's 1 light second in length. And it's going to put a shine light backwards, and it's going to hit the front, which is 0 on the light speed. And then it's going to have a mirror, and it's going to shine it back, and it's going to hit the front at 1 light second distance. And this one's going to occur, it's going to take 1 second to go that back distance, and then it's going to take 1 second to go that front distance. Okay, so it's 1 second light speed and 1 second. So of course, its speed of light is c. But with alt, that's not the case. So here, if this is 1 light second and they're putting light in the backwards, it's only going to take 0.4 seconds to hit the back. And then when the mirror hits it and it goes forward, it's going to take 1.6 seconds to reach the front. So the speed light's not constant. It's faster than c in the back, and it's slower than c in the front. But here's the thing: when you consider the two-way speed of light, it's going to go 1 light second forward. It's going to go 1 light second back and 1 light second forward, and it's going 2 light seconds total distance, and it's doing it in 2 seconds. So the speed of light in the two-way speed of light is constant, but the one-way speed of light is not constant. Okay, here we're looking at a moving platform over time. And for special relativity, you can see that the time is earlier offset by the relativistic time offset in the forward direction. But for alt, the whole platform is at the same time, and there's no relativistic time offset. Okay, so it turns out that these equations, and we were the first ones to show this, that if you take this RTO, which is basically differential simultaneity, and you remove it from the LT time coordinate equation, you just subtract it, this equation will turn into the alt equation. And conversely, if you add the relativistic time offset, how much time is offset with distance, from the alt equation, then, I'm sorry, you add it to the alt equation. It wasn't there before, and you've added it. This equation will turn into the LT equation. Okay, so these are basically, and because all of the other equations are the same, just by removing differential simultaneity or adding differential simultaneity, you can convert these two transformations into each other. So they're sister transformations in which time is offset with distance or time is not offset with distance. Okay, so how can we experimentally distinguish special relativity and alt? Well, from the stationary perspective, you cannot distinguish them because they both have relativistic effects, and those relativistic effects are identical. But from the moving perspective, like if you're in a moving spaceship or a moving, rotating planet, from the moving perspective, the special relativity and alt do differ. And as we went over, special relativity, one-way speed of light is constant, and the alt one-way speed of light is not constant. On the other hand, in addition, special relativity has reciprocal relativistic effects, and alt has directional relativistic effects. So you're like, what does that mean? So let's look at it on this diagram. Here we're going to be looking at time dilation. So at time 0, the moving frame and the moving frame and the stationary frame are both at time 0. So at 1 second in the stationary frame, the stationary observer can look across and say, well, what time is there in the moving frame? And while it's 1 in the stationary frame, it's 0.8. So he's like, whoa, time is going slow in that moving frame. But here, the moving observer, it goes to 1 second, and it's going to look along its slanted timeline at the stationary frame, and it's going to say it's 0.8. And it's going to go, whoa, time is slow in the stationary frame. So it's reciprocal. Okay. Both people are going to be looking at the other frame and seeing time slow down. But with alt, that doesn't occur. So here they're both at the time origin, and at 1 second, the stationary observer will look across and say, yes, it's 0.8. They're time dilated. But the moving observer at time 1 will look across and say, whoa, it's 1.25. Time is actually contracted. Okay, not dilated, it's contracted. It's going faster in the stationary frame. So both these observers are going to agree that time is going slower in the moving frame. So it's directional. Okay, here's a spaceman floating in the middle of space. And if we look at special relativity, if another spaceman is whizzing by him to the right, this spaceman's going to go, whoa, your clock is going slow. But in special relativity, everybody in the inertial reference frame can consider that they're at rest. And so this spaceman thinks he's at rest, and this other spaceman is going by in the other direction very fast. And he goes, no, your clock is going slow. So there's a disconnect. This person thinks this spaceman's clock is going slow, and he's saying, no, your clock is going slow. So that's reciprocal time dilation for special relativity. But with alt, this spaceman would see this other spaceman going by and say, your clock is going slow. And this spaceman would look at this spaceman and goes, well, your clock is going fast. So they're both agreeing that this spaceman's clock time is going slower than this spaceman's clock. So then you can ask yourself, well, why isn't it reciprocal? Why is one person going faster than the other? And so that's what we're going to have to address right now. What determines who is going fast or slow with alt? Okay, so here we have, so it turns out that what determines the speed with alt is going to be velocity relative to a preferred reference frame, or PRF. So you can imagine this whole orange glow is the preferred reference frame. And so this spaceship is going relative to that, and it's going to be contracted in the direction of motion, and its time is going to slow down based on its speed relative to the preferred reference frame. Okay, so initially, publications had suggested that the preferred reference frame for alt would be the cosmic microwave background radiation. So this is the remnant of the Big Bang. It used to be superheated. It's now cooled down to microwave energy, which is pretty low, and it fills everything in the universe. And it's very uniform, and they've just blown up the little differences to show it to you here. So, but it turns out that this cannot actually be the preferred reference frame. So one thing is we're moving relative to the CMB at 370,000 meters per second. And the reason why it can't be the preferred reference frame for alt is because relativistic experiments have ruled out a PRF, preferred reference frame, that is external to the Earth. So here we see the sun and the Earth, and this CMB is moving 370,000 meters per second relative to this thing. And the Earth is going to be moving around the sun at 30,000 meters per second, and it's going to be rotating in different, depending on the latitude, but at the equator, it's 465 meters per second. So sometimes the Earth is going to be moving with the CMB, which is going to reduce its velocity relative to the CMB. And at other times, it's going to be moving against the CMB. So it's going to have a greater velocity against the CMB. So relativist experiments have said, we don't detect those changes in velocity, okay? So there is no external preferred reference frame that would work for alt. So in 2014, I proposed that PRFs for alt are locally associated with gravitational centers. So if you look at a solar system, every planet is a local gravitational center, and it's going to have a preferred reference frame around it. Now, if you're far away from a planet, but you're in the solar system, then the preferred reference frame is going to be the preferred reference frame of the sun for that solar system. So for the Earth, if you're near the Earth or on the Earth, the preferred reference frame is going to be the Earth-centered inertial, or ECI, reference frame. So this is a well-known reference frame, and it's not rotating. It's non-rotating. So as the Earth is rotating, that velocity, that rotational velocity, is going to be an actual velocity relative to the preferred reference frame. But as the Earth goes around the sun, there won't be any velocity, because as the Earth moves, well, the ECI moves with it because it's centered on its gravitational core. Okay, so the only velocity we have to worry about here is the rotational velocity of the Earth around its axis. Okay, so what's the evidence that the ECI is a preferred reference frame near the Earth? So one is that time dilation is relative to the ECI, and that was measured with airplanes. So in 1972, Hayfel and Keating did their famous experiment where they took atomic clocks in the US, and they had lots of atomic clocks, and they took some of them and they put them on a plane that's going to go eastward. And they took some of the clocks and they put them on a plane that go westward. But before they put them there, all the clocks were synchronous. And they left some of the clocks on where they started. And so they then put these clocks on the eastward flight. It's going to go around the Earth, and it's going to come back to the US. And then the westward clocks are going to go around in the westward way and come around and come back to the US. And then they're going to take the clocks off the planes, they're going to put them next to each other, and they're going to say, what's the time on the clocks and how do they vary? And so what they were calculating that this time dilation was going to be relative to the ECI, the Earth-centered inertial reference frame. And keep in mind, the Earth itself has a velocity as it rotates relative to the ECI. So the Earth's velocity for their experiment was 361 meters per second relative to the ECI. The eastward flights are going faster because the Earth is rotating, but the flights are actually going faster in that direction. So that was 604 meters per second. And the westward flights are slower because while the Earth is turning relative to the ECI, they're actually going in the opposite direction. So that was 143 meters per second. And then they calculated, well, how much time dilation do we expect based on the velocity versus the ECI? And what they observed was exactly what they predicted. So the eastward flights had a slower time, less time compared to the Earth clocks because they were more time dilated because they were going faster. And the westward clocks, they were faster relative to the other clocks because they were going at a slower velocity relative to the ECI, so they had less time dilation. Okay, and then another evidence that the ECI is a preferred reference frame is time dilation of GPS satellites is calculated relative to the ECI. So these GPS satellites are moving at 3,900 meters per second, and you can calculate based on that speed relative to the ECI, and not relative to the rotating Earth, but relative to the ECI, that they're going to lose 7 microseconds per day due to this velocity-based time dilation. And without correcting for this time dilation due to velocity, GPS will be off by 2.1 kilometers per day. So every day it'd be off by 2.1 kilometers, 2.1, 2.1, and it wouldn't work. So basically, but you know, in the reality, they're also time contracted due to being higher away from gravity. So gravity also causes time dilation. And so they're time contracted, but those are additive effects. So that's like 46 microseconds per day faster due to gravity, and 7 microseconds per day slower due to velocity time dilation. So you add them together and it's 39 microseconds. And the fact that they're different, that they're additive, means they're separable effects. Okay, and then the last one is that the one-way speed of light is relative to the ECI, not to the rotating Earth. So Allen et al. In 1985 did an experiment where they sent light signals to GPS satellites around the Earth in the eastward direction. And what's going to happen is, as this light is going around the Earth, the point where it was emitted is going to move to the east. And so it's going to take longer to hit that position. And so if you were considering it from the Earth perspective, it's not constant. Okay, you send it to the east, it comes back to you, but it took longer than you expected. So it was slower. The speed light was slower. And then if they send it out in the westward direction, now this point is also moving this way, and it's going to come back faster. And so you would say the speed light is faster in the westward direction. Okay, so we wanted to measure the offsetting of time with distance in a linear trajectory. So linear. And we wanted to do it linear because special relativity has historically proposed to work in these inertial reference frames, which are linear constant velocity trajectories. But there's a problem in terms of how you can synchronize the clocks in the two positions. So you have to, because the clocks are separated, you have to figure out how to synchronize them, make them the same time in the two directions. I mean, in the two locations. So Einstein suggested Einstein synchronization. And so what he said, he stipulated that the one-way speed of light was going to be constant. So he didn't know that. He just stipulated it. And he said, well, you can use that one-way speed of light being constant to send it from this clock to this clock. And then you just base it on that distance. And then you would set this clock based on that distance and how long it would take to go that distance. But the problem is that if you do that, you're going to be instituting the special relativity space-time, and you're going to basically be offsetting time with distance the same way the stationary observer sees that the time is offset with distance. So this is our strategy for determining how much time is offset with distance. So there's a laser, it's going to put out a light beam, and it says a vacuum chamber, and the light's going to get split by a knife edge prism. It's going to go in the two directions. There's going to be a receptor for the light at the two ends, and then there's going to be an atomic clock at both ends. It's going to put a timestamp on the light signal. Okay, so what we're interested in is how long does it take to go this direction, and how long does the light take to go this direction? And we'll get a timestamp for that. So how are we going to synchronize the clocks? Well, you'd have to put this apparatus in a north-south orientation, because if you put it east-west, well, the speed of light's not constant east and west. So you put it in north-south orientation, and you can set that knife edge prism so that you get exactly the same time going up and going down. Then, because we're interested in a linear trajectory, we can't put it on the Earth. The Earth is rotating. We're gonna have to put it in a spaceship and go in a linear trajectory, and then you can say, well, what's going to happen to the time on those two clocks that were synchronized here? Well, if special relativity is in effect, then the simultaneity framework is going to cause the offsetting of time to be earlier in the forward direction relative to the backward direction. But if alt is doing the simultaneity framework, there's not going to be any difference in them. Okay, so this is the experimental setup. So what's going to happen to the timing of those beams? So here we're looking at this experimental apparatus. It's sending light out from the center in the two directions, and this is for special relativity. And it's going to pick up. It's going to hit the two ends at some later time. And what you see is that it's going to hit this end and this end at the same time in the move-in frame. Remember, time is read off slanted in special relativity, so there won't be any timing difference. But if we look at alt, what we see is this apparatus is going to put out light in the center, but it's going to hit the back first, and it's going to hit the front later. And so there's going to be a clock difference for alt. And then if you just compare no timing difference for special relativity against this clock difference for alt, then you'll be able to know how much time is offset with distance. So it could be no timing, could be this clock difference for alt, or it could be something in between. So that experiment, this is what you would expect for going about 12 kilometers per second. So you expect about a 6 picosecond difference for the back clock relative to the forward clock for alt. So it would take longer to go to the forward clock and less time to go to the back clock. And then for special relativity, you would expect no picosecond difference. And so you could say, well, how likely is it that you could maintain, this clock synchrony from when you did it on the Earth to being in space? But the reality is you can just take this apparatus in the spaceship and you can just flip it, okay? And as you flip it, this forward clock, which had a later time, when you flip it for Alt, it's going to have a lower time now. Okay, so you can check to make sure that things are working correctly. And then the time difference when you flip the special relativity shouldn't change anything. Okay, clearly we didn't do that experiment because we're not NASA and we don't have a spaceship. So, but we did determine the offsetting of time for rotational motion. And the reason we can do rotational motion is because you'd only need one clock. Okay, so you can have an emission and reception point where you're sending light around a circle and it's going to come back, and the clock that's at the emission point will detect when it left and when it arrived. So you don't have to worry about synchronization of clocks. And so we did, so me and Riju Balachandran, who's one of my former grad student, we did a geometric proof, and what we're looking at is how much is time offset with distance, and we wanted to put it in terms of an anisotropy signal. And anisotropy just means how much time is, how much the speed of light, in this case, is offset from what you expect for it being constant. Okay, and we came up with this equation where m is the slope of the x prime axis, which tells you how much time is offset with distance. And for special relativity, that slope should be v over c squared. And for Alt, it's 0. And then this anisotropy signal in a rotating frame, that's going to be equal to the unidirectional Sagnac effect. So now I have to tell you what a Sagnac effect is. So the Sagnac effect is, here we're looking at a stylized satellites around the Earth, and the Sagnac effect is going to be sending light out and then asking how long does it take to come back. So here, light's going to go out. It's going to go in the direction of rotation, but while it's moving around the circle, the emission point is also moving, and so it had to go all the way around the circle and then further to come back to the emission point. And then here's going to be the Sagnac effect in the opposite direction. And so as the light's going in the opposite direction, this emission point is moving toward it, and it's going to take less time. And so it didn't go over a whole circle to get there. So that's the Sagnac effect in the opposite direction. But if you consider it from the rotating viewpoint, and you send light in the direction of rotation eastward, it's going to actually be slower to come around. And the Sagnac effect from the rotating perspective in the westward direction, with opposite rotation, is going to be faster. And so you're going to say, well, the light's faster in the westward direction and slower in the eastward direction. So here you can see the westward direction is faster, and it's going to arrive back at that point, and the eastward light is going to be slower. Okay, so we were going to plug in the unidirectional Sagnac effect equation into our thing, but the problem is that there's multiple Sagnac effect equations. So there's the conventional Sagnac effect equation, which is 4 pi omega r squared over c squared. And this is in polar units, which is rotational circular units. But this omega r just is the velocity, and 2 pi r is the length in the rotating frame. So this whole thing is 2 times v L prime over c squared. And this is basically 2 times that RTO value, but in absolute terms. So the signs don't match, but it's just twice the RTO. And this is linked to Alt because the Alt one-way speeds of light will give this conventional Sagnac effect equation. Now, there's also the Galilean Sagnac effect equation where there's no relativistic effects, and it's going to have the same equation except there's an extra term in the denominator. And then if you take 2 other rotational transformations, the Langevin metric and the post-transformation, they're going to have a different term in the denominator. So how do we determine which one is correct? Which ones are valid? And it turns out that the Sagnac effect is coming from the forward one-way speed of light and the backwards one-way speed of light, or rotating and counter-rotating. So, but if you take any forward speed of light and any backward speed of light, then you'll get a 2-way speed of light that's specific. So we can deconstruct from these and get the 2-way speed of light that corresponds to each of these Sagnac effect equations. And for the conventional Sagnac effect equation, the two-way speed of light is c. Speed of light is constant. And for the Galilean and the Langevin metric, it's not constant. But the two-way speed of light has been measured to very high resolution. So this experiment in Germany measured a delta c over c, which is how much it differs from the speed of light divided by the speed of light, and it was 1 times 10 to the minus 18. So that's very high resolution that there's not any change from the two-way speed of light being constant. But if you use the same conditions and apply them to this Galilean two-way speed of light or the Langevin metric two-way speed of light, you get a variation of 4.4 times 10 to the minus 13 or 8.8 times 10 to the minus 13. And these things are 10,000 times higher deviation than was found for the actual experiment. So we know that these are not valid. They're not correct Sagnac equations. So the only one is the conventional equation. So here's our equation that's linking time offset with the anisotropy signal of light. We now know the anisotropy signal is half of the Sagnac effect. So we can put this equation into polar terms. We can plug this into the anisotropy signal, and what you get is that the slope is exactly 0. So that means that there's exactly 0 offsetting of time with distance in a rotating frame. Okay, so is differential simultaneity in rotating frames? So our measurement says, no, it's not. There's no differential simultaneity in rotating frames. We measured it and it's 0. But there's some other papers, there's like 5 papers that have proposed in the past that if you look at a rotating circle, that you can put co-moving light, and so these are like little co-moving reference frames around it, and you can do an infinite number of them, and in each one of these co-moving frames, the speed of light is constant. Okay, but then you say, well, how do you go from that to a Sagnac effect? And what they did was they either integrated those linear one-way speeds of light, or they did the velocity addition formula, or they used geometry, and they all produced a Sagnac effect. So it's sort of surprising. They start off with a constant speed of light, and they end up with a Sagnac effect timing difference. But this equation, we've already seen it before, and that equation is invalidated by the two-way speed of light. It gives you a non-constant two-way speed of light. So all of these papers don't match reality. This whole approach doesn't work. And then 6 other papers have said there's a time gap created by the RTO, the relativistic time offset, that's going to generate the Sagnac effect. And what they're looking at, if you have a cylinder and you say, well, time is going to be offset with distance. So if you just think about it and you start off at this point, by the time it comes here, you're going to have an earlier time by the RTO. But the problem is that they're trying to say that earlier time is the Sagnac effect. But the Sagnac effect, if you send light around a circle, it's going to take longer. There's going to be a delay to catch the front. Okay, that's a positive difference. But this RTO is a negative difference. Okay, so they published these papers, but they didn't realize that the signage was opposite. Okay, the Sagnac effect is plus VL prime over C squared, and the RTO in the direction of rotation is minus VL prime over C squared. And in fact, the reason they're opposite is because the RTO, if it made the time earlier, this later time would make the speed of light constant. But because the speed of light is not constant, it takes longer to go there, then you can actually infer that the RTO is not present to make the time earlier. So it's actually evidence that there is no RTO, or relativistic time offset. Okay, so now we can even ask, is there any evidence for differential simultaneity anywhere? And so 2 hallmarks of differential simultaneity lack all evidence. So there is no data for the constant one-way speed of light in a moving frame that is not an alt PRF. So people have said, well, people see that the speed of light is constant in ECI. Well, yeah, but the ECI is a preferred reference frame for alt, where the speed of light is also going to be constant. But there's nothing in a moving frame, moving relative to an alt PRF, there's no data in existence. And then there's no data of reciprocal relativistic effects in any context. So this is where two people are moving relative to each other, and they're like, you're time dilated. No, you're time dilated. That's never been demonstrated, okay? Even though this is a hallmark of special relativity. And then I had a paper in 2024 where I'm gonna say, well, alt and the LT or special relativity only differ based on differential simultaneity. And so if alt can explain an experimental result, like a relativistic effect, then that implies that differential simultaneity is not present because alt doesn't have differential simultaneity. And I was able to take all of the relativistic experiments, different types of relativist experiments, and put them into 6 categories of how they are explained by alt. So I'm not going to go over all of them, but I'm going to go over like 3 of them. So the first one is experiments not relevant to alt or the LT. So these include a lot of, experiments that have nothing to do with it, that are testing different weird aspects of potential Lorentz invariance. But there's also tests of gravity. Gravity has relativistic effects. And the reason why it's not relevant to alt or the LT is because alt in the LT or alt in special relativity don't deal with gravity, okay? They're dealing with motion, not with gravity. And another reason is because Tangerlini in 1958 showed that alt, just like special relativity, is compatible with general relativity in the absence of curvature. So if you take general relativity and get rid of curvature, people think it's only the LT that you get special relativity, but in fact, you can also get alt. You get alt also. So both of them are compatible with general relativity. So any general relativity gravitational observations don't invalidate alt. And then there's these null results for relativistic experiments. So there's certain experiments that have what's called null results. What that means is that no matter what the velocity is, could be slow, could be fast, the result of the experiment's always nothing, no change. It's always the same, okay? So some of these are like the constant two-way speed of light. No matter what speed you're going, the speed of light's going to be constant. There's other ones, Michelson-Morley, Kennedy-Thorndike, Moss-Bauer effect, optical resonators. And me and Ridju spent a lot of time going through multiple ones of these and explaining how it turns out that alt and the LT here actually a whole host of kinematic effects or like of relativistic effects, like time dilation, length contraction, the Doppler shift, the aberration stellar angle. So all of these relativistic effects, some of them in different combinations will produce these null effects. So like the constant two-way speed of light, you only need to have time dilation and length contraction. But optical resonators, you need four of these effects to produce a null result. But all of these were shared by both of them. So both alt and the LT explain why these null results don't happen. I mean, why they always happen as a null result. And then there's experiments that indicate no differential simultaneity rotating frames, and that's what we've been talking about. So this actually is opposite. It argues against the LT, and that's like directional time dilation, the not constant one-way speeds of light, or the Sagnac phase shift of neutron or atomic wave functions. So what are some possible implications of a different spacetime? So what we're talking about is spacetime. Well, spacetime is the most like basic thing in the universe. Everything is built on spacetime. And we're talking about a very big difference. Time is offset with distance or it's not. Okay, are there any potential implications of this? So I've only come up with 2 of these things. So one is that there's multiple unification theories. So these are attempts to unify gravity and quantum mechanics. And they have potential conflicts with differential simultaneity. And so they're suggesting violations of Lorentz invariance, which means because there's differential simultaneity, and they're saying, well, this causes a conflict. And so these unification theories are string theory, non-commutative geometry, loop quantum gravity, and warp brane models. And so potentially removing differential simultaneity from consideration could remove impediments to these theories, allowing gravity to be unified with quantum mechanics. And then I don't really have time to go over this in this seminar, but I have a paper from 2014 that said if you take directional time dilation, which alt predicts, and apply it to cosmology, it's going to produce an alternative explanation for dark energy. So instead of having dark energy, you would have time dilation in the present universe relative to the past. So the past would be time contracted, things would go real fast, and now we're slowed down because of time dilation. And these are supernova, and this is a line of redshift and distance modulus, and these supernova being off of the line relative to the straight line is why people think that's the most direct evidence for dark energy. And if you take into account the time contraction was in the past, then these supernovas are going to be shifted over directly onto the line. And I've now done this with this was from 2014 data. I've now done this with new data, which is even better, goes further, it's tighter, and now the link, this fit is the same as current cosmology. It's exactly the same or better than current cosmology like lambda CDM or WCDM models. Okay, so coming back to Galileo's relativity principle, it's basically saying one thing that it does say is that if you're in an enclosed box, you're going to an inertial reference frame, you cannot even tell that you're moving. Okay, you can consider yourself at rest, and everything is going to happen like you're at rest. But clearly, in this scenario where the boat is on the ocean of the rotating Earth, you can use the one-way speed of light to tell if you're moving. So the one-way speed light is going to be slower in the westward, slower in the eastward and faster in the westward. But again, it's this Galileo relativity principle is now only supposed to be going for inertial reference frames, not on a rotating Earth. Okay, so in conclusions, we measured how much time is offset with distance in rotating frames, and we found that there's exactly zero offset of time with distance. Galileo's relativity principle and special relativity do not hold in rotating frames because they lack differential simultaneity. Alt, which does not have differential simultaneity, is consistent with current relativistic data. Therefore, the available data does not provide definitive evidence for differential simultaneity. And we created a strategy to test if differential simultaneity is present in linear constant velocity trajectories using a space-based experiment. So we'd like to determine if differential simultaneity is present or is not present in inertial reference frames. And I'd like to acknowledge Riji Balachandran. She was a grad student in my lab. She's like an algebraic genius at doing algebra, which was super helpful. And she also loves doing puzzles. She's very quick and able to solve things. And we had lots of puzzles that we had to deal with in our 3 papers together. And I'd be happy to take any questions.